Hello, my name is Dan Nicholson, and I'm an assistant professor in the Department of Philosophy at George Mason University. This term, I've been fortunate enough to be one of the visiting research fellows here at Pittsburgh Center for Philosophy of Science. And honestly, I couldn't have hoped for a more stimulating and enriching environment in which to do my work. Now, my research is perhaps best characterized by a strongly interdisciplinary engagement with the conceptual foundations of the life sciences, an engagement that seeks to combine and integrate historical, philosophical, and theoretical perspectives. Now, much of my recent work has been devoted to exposing the fundamental problems with the appeal to engineering metaphors in cell and molecular biology. It's become apparent that machine analogies and machine models are more likely to deceive us than they are to help us in the elucidation of molecular and cellular processes. Yet despite this, the machine conception of the cell continues to provide the basic ontological understanding that many molecular biologists presuppose in their work. For many of them, it just seems natural to think of the biological as mechanical and to assume that the organization of living systems is somehow reducible to the individual structure of macromolecules, which are deemed to interact with one another deterministically, just like cogs in a machine. When alternative explanations of cellular phenomena are proposed, even when they're well supported empirically, they tend to be viewed with suspicion, if not ignored altogether. So what I've been trying to do in my time at the center is to work out why this is so. What makes molecular biologists so hesitant to consider non-mechanical, non-reductionistic, non-deterministic explanations of the phenomena that they study? And my working hypothesis is that it has a lot to do with the influence of a very famous book, namely Erwin Schrödinger's What is Life? The Physical Aspect of the Living Cell, published in 1944. Now, what's interesting about this book is that most of the founders of molecular biology at one point or another have recognized being influenced by this book, have admitted that. And yet the consensus among historians of biology since the 1980s is that the importance of the book was only recognized after the fact, retrospectively, when these molecular biologists started mentioning the book in their Nobel Prize acceptance speeches and in other autobiographical accounts. The contention is that the book was only used to confer legitimacy on the narrative of this new science that they had created by associating it with the intellectual authority of one of the greatest scientists of modern times, Erwin Schrödinger. Now, what I've been arguing is that, against this consensus, is that the influence of the book was not just historiographical, not even primarily historiographical, but was actually scientific, in the sense that the argument presented in the book, shaped the way molecular biologists construed and thought about macromolecules for half a century. So in a nutshell, what Schrödinger argues is that macromolecules need to exhibit an extremely rigid static structure, because only then can they be stable enough to withstand the disruptive effects of Brownian motion. Now, he puts forward this case so eloquently and so forcefully in the book that my contention is that molecular biologists thought that this argument provided a license for them to only focus on the structure of these macromolecules, DNA and proteins, and just to assume that the function could be read from the structure, and also to assume that one could understand these macromolecules without taking into consideration the cellular context. And it encouraged them to develop highly idealized deterministic understandings of the pathways and mechanisms that make up the cell, that underlie cellular behavior. Pathways and mechanisms that even today are problematically construed as fixed solid-state circuit boards, which seem to be intentionally modeled after those you find in electronic and mechanical engineering. So zooming out a bit, I've also been thinking a lot about what this particular case of Schrödinger and molecular biology tells us more generally about the history of the relationship between physics and biology in the 20th century. Because what's fascinating is that Schrödinger's view of cellular order, which is deterministic and mechanistic and reductionistic, replaced an earlier organicist view, which was none of those things, which is in fact processual and dynamic and systemic. And in fact, it was a view that had much more in common with, was much more closely aligned with the new physics exemplified by quantum mechanics. And what's interesting is that many of these physicists, like Niels Bohr, Pascual Jordan, Max Delbruck, physicists interested in biology, were convinced that biology would follow physics in emancipating itself from the shackles of this mechanistic, deterministic, reductionistic framework. the revolution was imminent, and yet when the revolution finally did arrive in biology in the form of molecular biology, it was a revolution that was based on the old physics. It was the old 19th century deterministic physics that ended up providing the foundation for molecular biology. So this is a really striking and almost paradoxical development in the history of biology that really hasn't received much attention. And I think it's a shame, because it helps us understand the reticence, the resistance of biologists over the past half a century to consider the relevance of ideas from non-classical physics in understanding how cells operate, how molecules interact in the cell. And interestingly, what's really exciting is that these ideas are today being picked up more and more by biologists. So that's really exciting.